finally the conclusion. Okay, first I will. So this whole robotic system is about for a disaster response challenge in World Robot Summit. This aims to accelerate the social implementation and research and development of robot in real life, social and industrial fields. So World Robot Summit is held once per 2 year. It was held in Tokyo in 2018. It would be held in Fukushima robot test field in 2020, but due to the pandemic situation, it postponed to 2021. Okay, so let me discuss about what is standard disaster robotic challenge of a robot summit. This whole robotic system we made is to participate this standard disaster robotic challenge. There are 5 main tasks. Uh, if we make a robotic system, the robotic system should uh, make to achieve these 5 tasks. First one is called negotiable. I will call it A from this figure. Stage that test whether the robot can pass through a narrow space. Then the B meter value, the second one you can see from the B figure. Um, that stage reads the value of the meter by turning the valve or lever. So first it should turn in the valve or lever, then the robot should be able to value. Then the C stairs and is tested for stability on unstable uh, scaffolding. So it will test that the robot is stable through the unstable area. The D, L-shaped debris on uneven ground. It tests that grasping and operating the pipe with the arm. And the final one, large area inspection, test that should read the QR code as in this figure and make a map, make a large area map, 3-dimensional map of the wall. So those are the 5 tasks that the robotic system should achieve if we want to participate in this challenge. So methodology. So making such a robotic system uh, participating in such a challenge, it need to manage teams. So one cannot be done such a system. And also we should select the proper hardware, and also we should select proper software development. Okay, so let's move to managing teams. No, normally, usually about 10 students in robotic engineer lab were involved in software development and carrying out operation of the robot. The team usually patrons the robot in an environment that imitate the previous version of it means we are currently patroning in the environment of 2018 World Robot Summit challenges. So each of the teams was led by final year undergraduate. It means fourth year undergraduate or a master's student. So rest of the students are going to operate the robot. Uh, and also if a student found a research teams or topic related to this each of the challenge, they will implement that robotic system, that specific software as a research. So the issues that comes when patricing were divided into long-term, medium-term, and short-term, and they will solve accordingly. Uh, in the future, the goal is to improve capabilities of the robot by improving software and fine-tuning software. And we also plan to implement this robotic system as semi-autonomous. And also, there are 2 main groups in our laboratory. First one is um, STM, we call STM. That is the team we are in. the team is working with actual robotics, and the other is IM simulation. They are doing simulation task. So selecting hardware. So this is the whole robotic system. Um, the whole robot uh, we use. So let's discuss about hardware one by one. For the crawler, we use disaster response robot called Giraffe. Um, that was made by Isaac Private Limited in Fukushima with the collaboration of our lab. It is a crawler type robot which has two main crawlers and four sub crawlers. Those four sub crawlers can work individually. And we use a flexible arm for the arm operation. We use Kinoa Jaguar with 6 degrees of freedom with curved rest. Uh, and also we use InterRealSense D435 for the depth camera. Uh, we, we should use a depth camera for the large area inspection task to create point cloud data files. For the we use arm camera for read meter value and also control the arm. And also we use two 360-degree dual lens camera uh, in left and right, and also front and rear cameras. For those four cameras mainly used for teleoperate the robot. And also we have arm PC to control the arm, and also this PC will gather the point cloud data from related camera. For that, we use a rubber grip to uh, increase to grasp tightly the objects. Okay, so that is the robotic system. For controlling the robotic system, we use a standard normal also a controller for its teleoperation side. And we use wired connection. We use wired connection instead of Wi-Fi because wired connection is reliable. The whole system we call Spider 2020. Let's move to software development. So we use to control and software integration the RT middleware technology, OpenRTM-based. For the camera viewer, we used uh, SDK called NDI. So why we use OpenRTM-based? So we used OpenRTM-based instead of ROS, robotic operating system, due to the high responsiveness of the OpenRTM-based than robotic or ROS systems. So in this kind of robot, the high responsiveness is really useful. So that's why we use that. So in this figure, you can see the diagram of the OpenRTM-based we used. So in OpenRTM, the function element in the system are called as robot components. By connecting those components, it is easy to configure a system that applied robotic technology. For example, you can issue the command from the controller to the robot or check the robot stats of the PC. So these are the components, and it is easy to distinguish. You can also distinguish. So the flow of the command flow of the robot from this diagram. Okay, so the camera viewer. So using NDI, we were able to view data and also multiple sources. So in this figure, the second figure you can see, in first figure you can see the control. The operator calling this screens, and also you can see in the second figure there are multiple screens. So the operator can gather multiple data from multiple camera view. So this is a summarized Spider 2020 system overview. In the system, there are three laptops, three PCs. I will show in here. Okay, so this is the first one, and second one is the ARM PC. Other than that, there's another PC inside this disaster response robot called Giraffe. Inside this, there's another PC. That PC is for the controlling the roller. Okay, so both all of them using Ubuntu 18. So this in this diagram of our software system, hardware devices are colored by red. OpenRTM is colored RTM components, associated with NDI is colored by light yellow. So this is the system. Okay, let's move to results. So we tested our robotics system in last year, November 7 to 8 at Fukushima field as a demonstration. So these figures were taken that function, from that function. From the second figure, you can see we used deep learning to identify value automatically, and this out shows the inspection. So I will later more video about this demonstration. So finally, the conclusion. So we used and also flexible arm and a lot of camera sensors, like 6 cameras. It was a wide area, makes Spider 2020 a complete disaster response robot. Hardware improvements are not enough to use robotic system in a disaster, and the software improvements should be done simultaneously. Dividing each task for different teams improved the efficiency of students, since each team needed improved background knowledge of specific narrow identifying issues, categorizing them, and continuously improving the system make the solid foundation event as World Robot Summit. So those are the conclusions we had from developing such a system to participate disaster response robotic challenge in World Robot Summit. These are the references from this presentation, and thank you, and also wait for the demonstration. Okay. I will show the negotiation task. You can see the this robot should go this narrow. That is the task. So I found for otherwise it takes some. Okay, so let's go to meter value. So you can see this operating meter value using so multiple screens. It's operating the robot. So the robot should turn on the lever, valve. Is completely manage this by teleoperation side, and you can see it automatically captures the meter value in here. Okay, L-shaped debris on uneven. What should pull that certain pole. area inspection. Okay, so this kind of wall we given, and this the QR code, and the robot will scan the QR codes, and in this in the real sense, the robot should we should make a, complete 3D map. Okay, so that's all my presentation. Thank you very much.
Thank you so much for a really interesting topic. A couple of minutes. I don't know if there is a question in the audience. Debo, I believe you're talking, but
I'm
your
sorry. I'm
microphone
sorry.
is.
Yeah, I was
Yeah.
mute. Sorry about that. So thank you for the very exciting talk. So I'm curious to know, what do the previous studies talk about the effectiveness of such systems in real disaster situations like flooding or fire, big fire breaking out, an earthquake. So in these situations, have you had a test with, or do you know about similar systems which worked on such situations, and what is the measurement of effectiveness of such systems?
Okay, so this actually this disaster challenge was created after the Fukushima Daiichi incident.
Mhm.
So in 2011, so in that incident, there were several tasks that actually Japan didn't have a technology, robotic technology for inspect robotic inside the nuclear power plant. So they had to they had some crawler type robot like sorry like this one.
Mhm.
So but they I think they have to make a disaster response robot as immediately. So they used that robot for inspect inside the uh, nuclear power plant Daiichi, Fukushima Daiichi. So they actually those that actually I couldn't remember the exact name of the robotic system. Um, so they used that inside there. So these tasks were made by according to those challenges they faced. Uh, Actually, you can see this meter value challenge is like inside. Suppose think about the inside the power plant, not a natural environment, artificial environment. Inside the power plant, these types are really useful. The turning lever or reading the meter value, and also this large area inspection. So if a robot can distinguish large area, like creating 3D map, what are the textures like that, it is really useful. And also that robotic system had this kind of functions. So that's why this basically this challenge was created.
So the
I think
radiation
I
being so high, radiation being so high
yeah.
inside the power plant, have you, how can you simulate such a situation in other places? I know you can probably simulate the kind of task, but if the radiation is so high, does that impact the functioning of the system that you are talking about?
uh, if it is really high, it
Uh,
would be effect. Uh, but we made robots, they also made those robots to for these kind of situations also, to capable of that kind of situations. So
But
actually I don't know the method they use to face those radiation. This actually, so this robot is also have some capabilities. This crawler, like it is waterproof like that. So one of these crawlers were also actively used for the disaster for currently in the Fukushima Daiichi nuclear plant.
Okay. All right.
Yeah.
Okay. Thank you. Yeah.
Okay.
Good. Good.
Okay.
Good.
Okay.
Thank you so much, Udaka. I don't know if there is any other question from the audience. If not, I would like to make just a quick question so we can move forward with the next presentation. Congratulations. I guess for most of us, at least for me, it's really exciting to see robots and this, and of course, like the you can the different ways that you can explore and the different things you can do the robots is amazing. From this picture, the one that you are at the beginning was kind of like small, but one the size it's not huge, but it was more than what it.
Yeah, it's like 100 kilograms.
How many? Sorry.
100.
It makes sense. How expensive it is, like to build a robot like that one, like an estimation?
Actually, that was funded by research grant. Maybe 50 million yen.
Okay. Okay. Okay.
Yeah. Actually.
Okay. It's okay.
Pretty expensive. Pretty expensive.
Yeah, I can imagine because that are just good. Yeah, John.
Yeah, just it's kind of nostalgic to hear about this robot research because I was at the time when during that period, and when the was made available by the national government and so on, and support from the prefecture and so on. This was always a very important and necessary Professor Naruse was commissioned with a responsibility to work on this. It's just amazing to see the progress. It's just really quite impressive, and it's really good work. And it's so good to know that this kind of advancement is being made. So well done. Thank you.
Thank you, sir. Thank you very much.
Okay, so thank you, congratulations on this work. So we're gonna move forward with the next presentation.
Okay,
so the next
stop
talk,
sharing.
it's sorry.
I will stop sharing. Okay.
Yeah, thank you. So the next talk is gonna be by Hiroki Ogawa, also work of Kito Shishiki Udaka, also Kitaro Naruse, and the name of this talk is Large Area Inspection Using 3D Point Cloud Data in a Disaster Response Robot. So all you guys, whenever you wanna share your screen.
Okay, I will share the screen. Can you see this slide?
Which black screen with many folders?
Black screen. Okay. S- Slide.
No, we don't see any slide.
Oh, okay.
Yeah, this is just a desktop.
Oh. Okay. Can you see
Yeah,
this
now
one?
we can see
Yes.
your.
Okay.
Yeah.
Okay. Now let's presentation. Okay. Hello everyone. My name is Kate Shishiki, and I am fourth year student of Department of Computer Science and Engineering at University of Oise. I would like to give a presentation on large area inspection using 3D point cloud data in a disaster response robot. This research was done by Hiroki Ogawa, Keiichi Shiki, Udaka Manaodu, and Professor Naruse Keitaro. Okay. So this section provides an overview of a presentation. It is divided into four sections: introduction, methodology, results, conclusion. Introduction. Okay. Yeah, inspection at WRS. It is necessary to use large area inspection remotely when man-made disaster. As an example, to inspect the inside of Fukushima Daiichi power plant, the research teams considered mounting sensor and cameras to robot for 3D mapping, which was and I defined it as a very good tool for understanding the disaster environment. Also, robot can be used to search for rescue people and survey disaster site, which can be expected to prevent secondary disaster and respond efficiently and quickly. For making such a robot, World Robot Summit WRS introduced Task EXP1. EXP1 means Explorer, and the standard disaster tasks in WRS. It was designed to inspect a large area and recognize targets that spread widely over flat and curved space, then generate a map of target quickly and accurately. The targets were given by QR code. According to the actual rules they were provided by WRS, the following instructions were given. My perception of QR is that they signify some kind of information at the disaster site. First, scanning should be started from the white box C figure. Second, the figure robot should investigate the wall area and create a large map of the QR code within the target. Third, the submitted map's quality of accuracy we thoroughly for the final point in the target. At the of the map is a result. I think this is meaningful that test our ability in the environment. Methodology. So, this is Spider 2020 robot system. The robot, the, the robot will be working with is Spider 2020, which was created through a collaboration between the University of Ice and the local company. The teleoperation system of robot consists of three pieces via router. The robot side has a PC to move crawler, arm, and camera, and the remote side has a PC to control the robot. Okay, the QR code, the zebra crossing is used for QR code detecting embedded in wall. Zebra crossing support encoding and decoding of 1D and 2D codes. We adapted zebra crossing because of its resistance to intrusive sunlight. So, flow of QR decoding. The image is binarized to emphasize the black and white. The QR code is detected from the finder pattern embedded in the three corners. So, right here is the right figure. Find the pattern red markers. To find the pattern is the mechanism that allows QR code to support rotation. So finally, check the decoding area and decode the QR code. So QR code decode methodology. So second, extension of QR code decode to increase decoding accuracy. Image processing using OpenCV to improve QR code decoding capability. So the noise is acquired image may affect the QR code decoding. Therefore, we stabilized the decoding with QR code by removing the noise. Next, trapezoidal correction is the performed to make the image from front size where QR code decoding is the most easily performed. So, merging data, merging point cloud data, multiple shots of the wall are required due to the complexity of the stage. We need merge PCD to make 3D map. What part used for merging data? So we use two data to first position coordinate of robots and but error is mixed. So data is generated from the camera and acted on by the actuator to the motor, but it does not work perfectly without errors. Therefore, the data acquired from the robot will be some errors. Second, data features. The walls and the features can hardly be detected. There are algorithms that use point cloud position to register to see. However, due to the use of point cloud features, this method becomes difficult when there are no features such as a wall. Merging PCD. Second, shooting from two perspectives far and near. The first, far PCD data. Small number of the feature is small number of data. The point cloud is cost. So it is easy to make clear 3D map. second, near using near PCD data, large number of feature is large number of data, and the point cloud is dense. It's possible to read the map sensitive to errors. We aim to use two advantage of these 2-point cloud data to generate the accurate map. Merging PCD methodology to merge PCD with QR as key to first detect QR from PCD data from far and near to by algorithm like shift. Second, merge PCD from far. Third, to tag the QR code and restore position of QR. To finally merge near PCD based on the information to like a right figure. In this way, two PCD data can be merged based on QR feature and the accuracy of environmental map generation can be improved. Result. Uh, Using zebra crossing extend its capabilities, we have successfully improved the accuracy of our QR decoding. During the preview, the 30 out of 20 QR decoding were successfully completed in a sunny environment. The number of QR code that can be read has been increased from the original zebra crossing library. Merging PCD. For PCD merging as in figure, we made a rough 3D map of the wall from distant viewpoint and held coordinate each QR in it. Next, they were shot from nearby viewpoint and merged based on the QR coordinate to create accurate 3D map. I think one of the discoveries is that the accuracy of environmental map generation has been improved by using population markers. Conclusion. The decoding capabilities has been improved by extending the QR decoding functionality. As a result, we were able to contribute to results of competition. In addition, the merging accuracy of PC point cloud data can be improved by including the position of PCD files in merging algorithm, and we would like to work together as a team in development and research to further improve the accuracy of QR code decoding and mapping. So, finally, merge video. So here is a video of merged PCD data. Now let's play the video. So, can you see the video?
No, we don't see the video. We can see only the desktop.
A desktop. Okay.
Yeah, now we see.
Yeah, now we can see the, yeah.
Ah. display the video. Oh, this is the taken at the different and angles from an RGBD the real sense. So it shows actual acquisition. As you can see, the point cloud is not very distinctive. Finally, merging data point cloud. The result is very close to actual design of the wall, and we have successfully generated a map of actual environment. Okay. Okay, thank you for watching my presentation.
Thank you so much. So we have also a couple of minutes, questions from the audience.
Yeah, thank you very much for your very exciting talk. And this is a very new area for me. I'm not much aware of the work that is done in here. So I'm just curious to know that you mentioned that it helps with the inspection of flat and curved surfaces. So I'm just trying to understand, if the surface is too complex, do you think the point clouds can take care of it if it is a very complex surface, many turns and things like that? Not really flat and curved, much more complex. This solution is still going to work?
そして、あ、やべえ、どうしよう。sorry. Sorry, one more question. One more time.
So what I'm trying to understand is, you mentioned in the beginning of your presentation that this point cloud system helps with you're probably taking care of the inspection of the flat and curved areas, right? Is that right?
Flat area.
Flat and curved
Actually,
areas, you said. So I'm trying to understand, if the surface is very complex, many turns and many obstructions along the way, this system is still going to work? That's my question.
Only only QR code existing area. We give algorithm to existing area.
So if the QR code existing area is too complex, is this solution still going to work?
Complex, but using
Can I answer for that? So the QR code is kind of a marker. So if there are a lot of QR codes, so it is easy to generate maps. So QR code has a position. So the use of is to distinguish the complex. So if you use point cloud data, like It's really identify each of. That's why we use cloud data competition. The QR code is kind of markers. So
Okay, so you can distinguish the simple
in
from the
maps.
complex areas using the many QR codes.
Yes.
Okay.
Yes. Yes.
All right. Okay. Okay. Thank you.
I have a comment.
Yep.
I just like to say, Shishiki-san, I remember you from my class, my English class. So
thank you.
congratulations. Congratulations on your presentation today. I thought your presentation, I'm just going to say something about your presentation only, not the technical side, but your presentation. And I could understand you, and I can see that you have improved since you were in my class.
Thank you very much.
Good, good, good.
You're welcome.
Thank you. Thank you very much.
Welcome.
Well,
You talked about Taiwanese mashoba.
Huh?
You presentation in my class on Taiwanese food, Taiwanese mashoba. Maybe you don't remember.
Sorry,
It's
sorry,
okay,
I
don't
have no
worry.
idea.
I think he's going through all the presentations that he has done in the university, trying to find that one.
It just shows how much progress he's made. Oh, that's good. Okay, interesting talk. Thank you.
Good,
Sorry.
thank you.
Thank you so much, Shishiki. Really, really interesting talk. So we're gonna move on with the last presentation of this first session. Daishi Shima, Tomonori Furukawa, Ryuma Aoba, Ayato Kota Suruno, Kitaro Narus. And the name of this talk is Team Activity of Robot Competition of Simulated Robot in World Robot Summit 2020. So whenever you want to start, guys.
Okay, can you hear clearly? Hear me? It's okay.
Yeah. Right. We can.
Okay, so, hello everyone. My name is Tomoyuki Furukawa, and from the Robot Engineering Tree of University. I'm the first year undergraduate student, and there are 5 student members in this group, and Professor Narse is a supervisor. So in this presentation, and Sima will speak. So we are going to start the presentation team. So this time, we would like to talk mainly about what is student doing for the WRS. And this title of the activity of robot competition of simulated robot World of Summit. So this is the contents of the presentation. So it is divided into 2 parts. So part 1 will be given by me, and part of 2 will be given by Daichi Shima. So the presentation, so the presentation is divided into 2 parts. So if the speaker change, the screen share change as well. So let's start with some background. Yes. First of all, we are participating in competition in this fusion from STM. Since participating as a competition, our objective is to work efficiently on the tasks in the competition. And achieve good result in the competition. As mentioned, mentioned earlier in STM, we own robots in our laboratory, and by using robot simulation, we can improve the practicality of the actual robot. So from this point of view, we need to develop software and robot model and so on. And there are several experiments to be used. We are using a robot simulated software called Choreonoid. And the robot models is controlled by PS4 controller, DualShock 4 controller. The diagram of the right shows the configuration. The loss, what is a loss? Loss is a middleware for robot, but it is used to communicate data from DualShock and camera image data in the Choreonoid. This is the environment in which we are developing the robot. We are also collaborating with the Japan Atomic Energy Agency, called JEA, and in the development of the robot model as a team of students. With their help in providing the software and these are what that using this time. And here is a simulated robot model. The side is a spider, the right side is a emu. So these are model with the help of these models were created with the help of JEA and providing in anything. Next is development about yes. So this is a general explanation of the development. So in order to achieve the high performance, so we worked on following two main points. So first is that we devised and developed the model, a robot model, development software to control the robot model. So this is a process of development. So first is I've created a model of the robot using a CAD and the tools. The second is develop software to control the model in accordance with Choreonoid. And the third is check the feasibility of the simulation. And the fourth is a graphic with external visualizer and using the loss interface to finally completion of development. Next is a tasks in this simulation competition. and the program and sorry is completion. This is the task. So in this competition, we should take 4 tasks. And first, task one is investigation and rescue of vehicle and surrounding. And task 2 is securing the road. And task 3 is firefight work. And last task is inspection of the tunnel wall and ancillary equipment. So next is program. We encountered several problems when we were doing. So first is in the task 1 and the task 4, there are many cylindrical objects with QR code at their ends, so which is almost impossible in existing robot models. And secondly, in the task 4, it is difficult to extend the arm to the QR code that exists on the top of the jet fan, so due to the size of the robot. And next is solution. So to solve the problems, the endoscope camera. So this has 4 joints which are controlled independently. In addition, we have developed a robot arm controller with inverse kinematics, which allows us to move a hand tip to designated position automatically. So as a result, we are able to solve most of the problems in task 1 and task 4, but it is still difficult to adjust the camera to find and focus to the QR code only looking at the endoscope. So now we are currently developing a robot arm controller to solve the new problem. So next is now I share talk. Next is Shimataichi.
Could you hear me and see the slide?
Yes, we do.
Okay. My name is Daichi Shima. I will present from the this slide. Okay. Activity. The actual date of the WRS was July 2020, but due to the COVID-19, it was postponed to May 2021. Therefore, we held a demonstration event in October this year to demonstrate the robot model and hand over the team members. For this demonstration event, the University of ICE created 2 participating teams. The first was a team of 4th years, second was team of 3rd year students. There were the teams that participating in this event. The demonstration event is composed of 2 phases. The first one is online challenge. We have organized a review committee separated from participating team. The committee has created a set of courses, opened it in GitHub, asked the participating teams to challenge them by their PC and to submit the result. The other one is online symposium by team to share the experience with this student with Zoom. Offline challenge. This is a photo shot to ensure that there are no irregularities in the task attack. The operation PC and the monitoring PC are separated, with one person acting as operator and one supervisor. On the operation PC, a user interface using the loss feature RBs is used to control the entire operation. The monitoring PC observer observes the entire field use Coronoid and monitors it for judging if the task is performed well. This is how the competition will actually take place in WRS. Okay. This is a trial course. SG1L course task is to make the robot run. SG2 course task is to move obstacle out of the path and bring a shape out. Okay. This is a screenshot of the trial as seen by the observer. It is also the one of the team A. This is a LU and the SG1 course. The spider and LU are being tried the both course. So this is a spider. Okay. This is a SG2 course and LU. So bring L-shape bar out in these tasks. Okay, next. This is a screen seen from the operator side. Multiple camera data and the robot status data are used to display on RBs. This is RBs is a loss too. This is a screen of the NDU in SG1 course. The spider is also operated by the operator with this kind of screen. Okay, next. Online symposium. Reflection on the trial that we had tried as a team in the form of presentation. Team A was a team formed for WRS 2020 and mainly focused on operation and development. The team was able to clear most of the challenges this time and proposed to focus on passing on the technologies to the general manufacture activities. Team B has been preparing from the WRS to be held next year. focusing on the activities of the operator and preparing for demonstration. The presented, they presented the improvement of the current system and operators, and presented their goal and improvement from next year's WRS. At the online symposium, we consider the holding over technologies be, team B to be the most important things. We hold a study session focusing on colloidal and loss among the students. Specifically, we teach Team B member how to create a model and development procedures. So at last, we have a reported activity on development and team training as an instance of project-based learning in robotics. This is reference. That's all. Thank you for listening.
Okay, so thank you so much for the presentation. We have a couple of minutes again also for questions. So is there any question from the audience? No one. Okay, so I guess everything was clear for everyone. So thank you so much, guys. Really, again, also really interesting talk. I believe that for everyone, just to look into simulations, robots, it's quite exciting. So we are done with the first session of the morning. Debo, I don't know if we should take a break or should we continue, keep going?
It's 10:45 almost, so I think we should keep going because we are slightly behind the schedule.
Okay. Sounds good. So we're gonna start with of this morning, Adaptive Systems Laboratory of University of Aizu. So the first talk is about collaborative learning algorithm implementation for COVID-19 diagnosis towards an AI-enabled real-time biomedical system. So right now, Xinshan P, Shishan Wang, and Professor Abdallah are gonna share to us their work. So anytime you wanna share your screen, guys.
Okay, just wait a minute. Wait, sorry, I have to turn on my video first. And then I start sharing my screen. Okay, I'll start my presentation. My name is Xin Xian Pie, and I'm a fourth-year student, undergraduate degree of University of Aizu, and from the Adaptive System Lab. And these are the people who helped me with the work. Also, I have the team members, but I did not include here, but they will present their part later. And my topic is called a collaborative learning algorithm for AI-enabled real-time biomedical system, or in short, AIRBIS. So AIRBIS is one project, and I'm a part of it. Wait, So this is the outline for the presentation. First, I'm going to talk about the introduction, which contains the background and motivation, and then the methodology, which has the federated learning, system overview, client server protocol, and real-time augmentation. And lastly, we have the evaluation and conclusion. First, the background. Yeah, in biomedical images diagnosis system, when the number of patients increases, as we can see the spread of COVID-19, for example, we can see that we need a like faster reporting system and accurate diagnosis like system. We need that, but in the conventional system, they still lack in these two principles. As you can see here in the picture, like in the hospitals, in big hospitals, people have to wait for their turn. So yeah, we want to decrease this bottleneck. So to solve the problems, the ARPs or the AI-enabled real-time biomedical system, which now we focus only on the chest X-ray images. So instead of normally the chest X-ray images is being checked by doctor or experts, and the results will be shown to you. And while you have to wait for that, but in this project we use the deep learning or deep CNN instead to diagnose these chest X-ray images and show results on the user interface. As you can see here, the patient will take the X-ray and it will be automatically diagnosed by the computer at the hospital site. Yeah, there are 4 parts in this project. The first part is the convolutional neural network architecture widget, and the second part is the interactive software interface to show the results, and the third one is the hardware acceleration of CNN on FPGA to speed up the inference speed. And lastly, which is my topic, which is the collaborative learning based on the federated learning. So what is the motivation for this work? Firstly, if you're from the machine learning, you know that to train a model, first you have to collect the data, and if it's not labeled, you have to label them yourself, and which is a highly cost and time-consuming task. And then for most of the medical data, images are stored across hospitals, and most of the time they are not shared or open publicly because of the privacy concerns. Due to this, the conventional training process usually is not optimal, and also it takes a long time for the real-world implementation. So as you can see here, first for the conventional training process, first you have to gather the data and then prepare the data and then train the model on a computer and evaluate the model. It usually takes long time. So we use this method instead, which is called the federated learning. So what is federated learning? Federated learning is actually first proposed around 2017 by the research group at Google. It was originally intended to use with the data on the smartphone or the mobile devices, which has a lot of data, but we can also use with the medical data, which also has privacy concern. So federated learning is a machine learning approach which trains you using the local data resided across the multiple edge nodes or the clients without transferring the data. So we only get the models from the hospitals. So this is a step. First, we have the server here. The server aggregator has to initialize a global model, and then the model is sent to all clients. And the clients will use the global model to train with its data and update its model locally. And then it will send back its local trained model to the server. And then fifth, the server will aggregate and update to a new global model. And the process will repeat multiple times until the model is or has enough accuracy. So for the fifth stage, how do the aggregator aggregate and update to a new group? So this is kind of the core algorithm for the federated learning or FL. As you can see here, W and B are the weight and biases of the model. N denotes the total number of data. Oh, sorry, I did not mention. Yeah, for the accurate or better performance, we have to also send the data size together with the model. So N here is the total number of amount of data. I denotes the ID of the client, and NI is the amount of data on client I, and K is the total number of client. So actually, when the amount of data on each client is equal, for example, this NI here is equal on all clients, so we can consider this to be a MapReduce distributed processing, which we can change the I over N to 1 over K instead. But this is like one case for the federated learning. It's used for the parallelism to speed up the training process, which is one of the characteristics of the FL. Next is the system overview of the FL. As you can see here, we have the user interface to show the results, and then we have the data model file folders or the database, and the script to train and communicate with the server will run independently of these two, and then it will communicate with the server to update the models. And next is the client-server protocol. Yeah, actually, there are many ways to implement this communication protocol, but I use the socket programming, and to handle multiple clients at the same time, I use the multi-thread in Python. And yeah, the process is similar to the one I showed you in the previous slides. Also, I use the timeout for the communication efficiency, because this is like the communication happen continuously or rapidly until the model converged. And yeah, the steps here is just for understanding this, what symbol is. But if you don't understand, you can ask me later. I'll skip this part. Next is the real-time augmentation. So augmentation, when the training data set is too small in machine learning, we use augmentation to increase the data size by creating the modified versions of the existing data. But for the FL system, however, the client storage might not be enough, and it's preferable that we do not change anything on the client side. So we use real-time augmentation instead. So what is this? It means that the augmented images are only created then dynamically during the training process, and it will not be stored later after the training process is completed. So there's no changes and to the client side, and the data size also increases, which can be done using a Keras function. It's similar to the GAN that it produces the data dynamically. Next is the evaluation part. So in the evaluation, I use this data, which is guided by Nakamura-san, a team member of mine. So there are two classes of this evaluation: the abnormal class and normal class. In the abnormal class, we have the pneumonia and COVID-19 data, and in the normal, we only have the normal part data. But because of the different size, the unbalance in the data side, I used augmentation, the fixed augmentation first on the normal training data set. Yeah, I used contrast and shifting on the normal training data, because the contrast and shifting are like the natural characteristic of X-ray when it is taken in the hospital. And yeah, these two classes, so I used binary classification, and the experiment was done using the TensorFlow for the training. Yeah, so this is the model for the evaluation, which is only a simple model, because in FL we want to have the model as simple as possible to reduce the training process as well as the communication cost. Yeah, the model is very small. The input size is only 64 by RGB channel, 3 channels, and only 3 convolutional layer and 2 fully connected layer. So about the collaborative learning parameters I used in the experiment, I divided the data into five clients. So actually the total number is here, 8,550. So divided by 5 is about 1,700 something. Wait. And if you know about IID, it means the IID stands for independent and identically distributed data, which means the data is like independent of each other. But in actual implementation, in real world implementation, actually the data should be considered non-IID, because every hospital may have different, only a bit different ways to take the X-ray, or the data size of the pneumonia or normal without pneumonia is unbalanced. But in this experiment, we considered IID, and I used the real-time zoom augmentation on the chest X-ray, because actually I tested many augmentation type for the real-time, but the most effective one is the zoom augmentation. And yeah, check chest X-ray, because I think because chest X-ray image are resized, making the features easier to extract it in the convolutional neuron layer. And yeah, also using the real time, it dynamically create the augmented images, which further improve the effectiveness. So what are the things that I measured? First, I compared the results of performance of the real-time zoom augmentation without using it and using it. Next, I increased the computational cost on client size, which can be done by increasing the number of epoch or decreasing the batch size, which I will show you later. And then I compare the result of the best model from conventional and FL approach. So the first one is comparing the real-time zoom augmentation. As you can see here on the right side, I did not use the real-time augmentation. As you can see here, the accuracy is around like 80 something, even if we use all clients. Like I use from one client, 2 clients data, 3 clients to 5 all clients data. And the accuracy is actually worse than only one day using only one data set on one client, because we use the real-time augmentation. And yeah, when the number of data increases, amount of data increases, the model accuracy also increases. Next is to increase the computational cost on client side. It can be done by 2 things. First, we increase the epoch size. Wait. As you can see here, when the number of epoch increases, we need less communication round to make the model converge. Yeah, 1 epoch needs more round compared to 10 epoch, but we have to be careful here, because if the number of epoch is too big, the averaging method is effective, or the model won't converge at all. And next, we can decrease the batch size. When we decrease the batch size, the number of batch increases. So in 1 epoch, the number of updates will increase. So we need less communication around when we use smaller batch size. Next, compare the conventional and the FL approach, or the collaborative approach. As you can see here, on the left is the conventional approach. In my own experiment, the best I could get is around 94 point something%. But for the collaborative approach, which I've done many times, and the best one I could get is around 95.66%. Yeah, it's sometimes higher. Actually, it was a surprise to me too that they could get higher accuracy compared to the conventional approach. And conclusion and future work. So this paper presented a collaborative learning approach on CNN implementation for pneumonia based on the FL. So the approach can achieve the competitive results compared to the conventional approach, while also preserving the privacy of the data. And in the future work, yeah, I think the communication protocol can be optimized even further, and then there are many ways to implement this. The one I did is just one of them. And also, I think it's a good idea to also learn the approach when using with the non-IID data set. Also, lastly, to do the real world experiment with local clinics and hospitals. yeah, this is the reference, and that's all for my presentation. Thank you for listening.
Thank you so much for quite interesting talk. So really good time for questions.
Okay. If anyone has any questions, please go ahead.
So this is the federated learning a very new concept, you think, or has it been around for quite some time?
The federal learning is, we can call it the distributed learning, and the idea was actually like 10 or more than that, maybe 20 years ago, but they did not use it with the what you call it, the neural network model. And before this, we also have the MapReduce distributed processing, but this method is not as good as the federated learning. The federated learning was introduced first in 2000. It was originally used for the data on the mobile devices, but we can use that characteristic for the privacy concern with the medical data as well.
Okay. So other than the medical data field, which other fields can make use of it?
All the field that require the private.
Oh, security,
for example,
privacy issue is big.
Yeah, for example, on your mobile phone, like that, something like that.
So when compared to distributed processing, how is federated learning is an improvement? Can you explain that point?
Yeah, compared to the MapReduce distributed, they did not use the number of data for the averaging method. They only use, because all data is divided equally. So they have one, for example, for client one, we have, for example, if we have 5 clients, we have for each, what you call it, unit, they will have K or 1 over 5. But when the number of data is different on all unit or edge devices, I think using the number of data will improve the model very much.
Okay. All right. So NI. All right. Okay. All right. Yeah. Very exciting work. Yeah. Go ahead.
I mean, yeah, the argument for it. Okay.
Okay. Thank you.
Thank you for the question.
Yeah.
Thank you so much. In my case, just a comment. It's congratulations. It's really exciting to see that efforts are being done towards good the pandemic that we're facing nowadays. So congratulations on your work. So any other? I guess we don't have more questions. Thank you so much.
Okay, thank you for listening.
So we're gonna move forward with the next talk, a comprehensive software study on classifications of COVID-19 solution networks. Yuka Nakamura, Professor Abdallah. Start, guys.
Slide.
Yes.
Thank you. Hello. My name is Miyuka Nakamura from the Adaptive System Lab in the University of Aizu. Presentation title Software Study of Classification 19 with deep computation. This is our outline. First, I talk about the introduction, and I talk about the dataset, and next, I talk about the evaluation of my research, the discussion, and I introduce a conclusion. And this is the introduction. The number of the is still increasing. The PCR test is the mainstream. Accuracy of the PCR test is 60% to 90%. And the accuracy of lung image taken by the CT scan is 80% accuracy according the diagnosis according to. From this paper, we consider that a lot of information for the diagnosis action. X-ray images diagnosis method makes the hospital free of the specific devices. Then we propose a system for the diagnosing from the X-ray image of the lung to enable more accurate diagnosis and assisting doctors. This figure shows the letter is a conventional diagnosis system, and light figure is our AI diagnosis system. Our work is roughly divided into two, and collecting published lung images to create a dataset, and creating a CNN model for diagnosing more accurate COVID-19 using that dataset. The collected images are formatted for running and augmented so that the number of images is not biased for each level. Then lung images are classified into two levels by the CNN. Preliminary to detect the COVID-19, we are classifying it into that is infected with COVID-19 or pneumonia. Normal level that is not infected with any of diseases. And this is the background of the convolutional neural network. We use the CNN to train and classify lung images. CNN consists of a feature extraction unit and classification unit. Extraction unit feature of image by convolution. In addition, an activation function that is in or enhanced of the output, and a proving layer is also used to make it robust. Sorry. The classification unit classifies a feature of the extracted image by the fully connected layer and outputs the results. At the time of the running, the classification accuracy is improved by the updating and repeating the weights of the feature extraction and the classification unit. And this is the dataset we are using. The Kaggle dataset is used the competition of the classification pneumonia X-ray images. And it was launched by the Mustafa, and it has a healthy and pneumonia images. And it was launched by, and the Kaggle dataset includes 1,300 lung image for lung. And so we tripled it, and the data has been funded with the zooming and the rotation. And the COVID-19 images are published by Professor Cohen. And we divided them for running as shown in this table. Next week, I talk about the evaluation of our experiments. And experiment 1 is compared the accuracy of 4 CNN models. And we use these, and we created a simple model based on the lineage. And it has a 3 convolution layer and small model. And we compare the BGG16 and the MobileNet and the inceptionless net version 2. And this is the environment of the Linet 3 is a small neural network, so we use a 64 by 64 3 input size. But other CNN is larger than the Linet 3 2 by 2 to 4 by. And learning parameters is shown. And result of the accuracy. The Linet 3 and the MobileNet and inceptionless net were able to binarize with approximately 80% accuracy. But since all the inference results shows the we can see the BGG16 results failed binary classification in the case of the optimizer Adam used. Then this shows the result that the optimizer has changed to SGD. This was a successful binary classification. The experiment results show the approximately 20% reduced the accuracy of normal X-ray images compared to that of abnormal. And also 80% accuracy does not meet our goal of the creating a more accurate model. So we try to augment the dataset in real time to improve the fundamental accuracy. Since all training data can be randomly generated for each epoch, it can be said that if 8,000 training images are trained by 50 epochs, we can get 400,000. So we can try the large big data for training. And this is a result of the real-time augmentation. The result was the 94.36% was real-time augmentation. The normal level improved significantly from the 64% to 86%, whereas the accuracy of the abnormal was the same and high. And this is a discussion of our experiment. Experiment 2 shows that the accuracy was greatly improved by improving the dataset. But a dataset contains the small images, such as like here, and the noisy image like that, including the medical devices, and the unclear images like that. If removing these obscure images gives higher accuracy, obscure X-ray images may not be suitable for machine learning for on CNN. And this is a conclusion. And the binary classification was possible for all models except PGG16 under the condition that the optimizer was set to Adam. And the abnormal level can get 97 to 100%, so very high. But the normal level 67% to 70% lower than the abnormal. And the BGG16 optimizer is the STD is better than the Adam. And real-time augmentation increased the accuracy from the 86% to 94%. And this is our feature work. The first, we tried to learning with the other CNN models and using the real-time augmentation and change the optimizers such as STD. And next, we have tried to investigate the effects of inappropriate images such as small or unclear. This is a reference of my our slides. Thank you for your attention.
Thank you so much, Miyuka, for a really interesting presentation. So we open a space for questions.
Just a quick question, very exciting talk, and this is not my area, so I'm not entirely familiar with exactly what you have done, but I'm curious to know that you mentioned about real-time augmentation. So with using CNN, this kind of CNN, so what I'm curious to know is what is the worst image quality that you can work with when trying to make a real-time augmentation with this CNN network that you're using, this type? What is the worst image quality that you can work with?
Worst image. That means that in the
so I know you're saying that with C, unclear image for humans, you cannot use a real-time augmentation, right? With C, you cannot use. So how good an image you need to start working with real-time augmentation?
Okay. First, we find the we get the first this accuracy, then we try to get a more high accuracy, then try to this real-time augmentation. Then we noticed that the accuracy, the data set is important to improve the accuracy. Then we investigate that we see the detail of the data sets. So then we notice that this data set has the small or unclear and something. So
so my question is, how do you decide which data sets you can throw away and it cannot be used? So the CNN does that, like that deep learning method. You can weed out, can throw out the data which you think is too obscure, right? Am I right in my understanding?
So what's the limit?
limit.
The limit of readability. In each individual X-ray, how do you know if the X-ray is definitely not clear or clear enough? Like this one's okay, this one's not okay, this one's okay, this one's not okay. How do you know the exact point where it's not clear enough? Is that your meaning?
Yes, exactly.
That C is not clear, and I can see with my eyes, but then the other one is more clear. So how does the system define the difference between clear and not clear?
Yeah. This unclear is see from human. Yeah.
Yeah.
So.
Yeah. Human. It's okay. Sorry. Go ahead.
So next we try to investigate the effects these images. So
so a person will decide this is clear or this is not clear.
Yes.
A person so a person must see it and say not clear. This one is okay. This one is not okay.
Yes.
So a person will judge.
Yes, personal judge. Yes. Then compare the without the unclear images and current data set.
Okay.
Okay.
Okay, so
now we understand that part.
Yeah.
Thank you.
So I guess we're gonna move forward with next presentation. We are a little bit behind the schedule. So thank you so much, Yuka, for your presentation. So next one is hardware acceleration of convolution neural network for AI-enabled real-time biomedical system by Okada Yuki, Jankun Wan, Ofbodo Mark, and Professor Abdallah. So all yours, guys.
Yes. So, hello everyone, my name is Yuki Okada. I'm from Adaptive STEM at the University of Ice. My presentation is hardware acceleration of convolutional neural network for AI-enabled real-time biomedical system. This is outline. This is background. COVID-19 is currently on the rise all over the world and has become a country around the world putting effect on a range of public health measures. The disease continues to spread, and as of January 26, 2021, the number of the confirmed the global case have raised to 100 million cases and 2 million deaths. Therefore, we launched the Airbus project. This is Airbus overview. Airbus is a system that accurately diagnoses COVID-19 medical image processing technology based on it combines the advantage of software and hardware to provide a smart biomedical system with real-time diagnosis and low power consumption. The Airbus project consists with hardware, user interface, and software. Hardware use FPGA to increase diagnosis speed. UI is interface design. Software is more accurate model design. So I am in charge of hardware improvement using FPGA. This is motivation. Accurate diagnosis and prompt reporting are necessary to combat with COVID-19. The use of FPGA may speed up the diagnosis compared to software. Real-time diagnosis system with high accuracy. This figure 1 is experiment of This is system overview. First, a user sends an X-ray image of the for the FPGA will send user whether it is normal or abnormal based on the image sent to it. First, I would like to talk about the CNN model used in FPGA. This model was designed for FPGA, but I was careful about when design was the simplicity of the model. I tried several image sizes when creating this model. It was this image size that produced the highest accuracy. Input size is 64 by 64. Output is 1. The image is X-ray image in grayscale. Activate function is ReLU. Accuracy is 94.79%. This is optimization with FPGA. There are 2 improvement conditions for acceleration using FPGA. First, optimizing data transfer in FPGA. Second, optimization through the use of pipeline and parallel processing. I would like to talk about optimizing data transfer in FPGA. I use the following for optimization. Direct memory access, combination of function in use, bulk data transfer and buffer. These optimization are optimized library provided by links. But this optimization is done by changing the source code to optimize it. The standard for selecting function is to choose functions that do not affect the system when combined. Next, I will talk about pipeline, parallel processing and pipeline processing. Again, the Xilinx library is used to optimize parallel and pipeline processing into circuit function. The yellow line is the declaration of the pipeline process. Depending on the value of this, the starting interval of the pipeline can be set. In this study, there was no change in speed when either value were changed. Red circle indicate parallel processing. There was a speed up in parallel processing by modifying the code rather than using the Xilinx library. This is performance evaluation. Table shows the result measured using all the optimized introduced earlier. In this case, the circuit function was 620. In this case, the circuit function was 510. In this case, the circuit function was 520. Table 3 shows the result of using and not using the combination of one function of optimization. I believe this is the result difference caused by the change in the base source code. This is complexity evaluation, implementation of convolution layer and pooling layer. Device is ThinQ UltraScale NP-SoC ZCU102. SoC 2019.1. Rule 4 is FPGA resource consumption. VRAM is 4.8%. DSP is 1.6%. FF is 2.2%. URAM is 9.7%. Figure 3 is an experiment figure. This is conclusion and future work. In this research, we focus on the optimization of data transfer method, pipeline processing and parallel processing to improve the speed of design. There is no superior on speed compared with the CPU and GPU. With the plenty of and we plan to further optimize the architecture to speed up the diagnosis. This is reference. Thank you for your attention.
Thank you so much. Okada, for the presentation. So we open questions from the audience. Mm. Okay, so I guess we can move forward with the next presentation. Again, thank you so much, Okada, for a really nice talk. So we're gonna move forward with the last presentation of the second session of the morning. Real-time hand gesture recognition based on deep neural network by Naoto Ageishi, Tomohide Fukushi, and Professor Abdallah. So whenever you want.
Okay. You did see this slide?
You can see the presentation.
Hello everyone. My name is Naoto Ageshi. I'm an adaptive systems lab at University of Aizu. My presentation title is real-time hand gesture recognition based on deep neural network. This is the outline for the presentation. First, I will talk about background and motivation, research goal, system overview, method, and evaluation. Finally, I will talk about conclusion and future work. This is the background. Deep neural network technology is used for autonomous driving of cars, games, monitoring, and recognition. The application of the gesture recognition system using various tools and algorithms, and its importance are attracting attention in robot control. As one of the gesture recognition tools, there is one called the EEG signal. An EEG signal is a sensor attached to the head that reads a signal from the brain trying to move one's arm and move the artificial limb from the signal. Figure 1 shows an example of artificial using EEG signal. Motivation. Hand gesture recognition is a crucial task in such as process control. We developed a real-time recognition system using a deep neural network as a first step for the research, in which a person uses a prosthetic hand with an EEG signal from the arm. This is research goal. We design a system that recognizes 10 hand signs based on deep neural network from the camera. In evaluation, the goal is that the model we create will have high recognition accuracy. This is system overview. First of all, shoot a video of hand gesture. First of all, shoot a video of hand gesture with a camera, and cut the video in one frame, and perform pre-processing. It is identified by deep neural network and what the gesture represented. This is method. We shoot videos with 10 different gestures. A total of 22 types videos were shot with different backgrounds. They were taken 140 by 480 and 30 fps. divide the video into training and validation and test dataset. 16 videos used in training, 4 videos used in validation, 2 videos used in test. The recorded video to an image. This is example of dataset. Figure 3 shows an example of 10 types of hand gestures. Take a gesture like this in front and shoot. Table 1 shows the number of training and validation datasets. Cut 150 images in one video. This is a table of CNN model parameters. We learned with an image size of 64 by 64 and RGB. Drop out layers after doing the convolution layers and the pooling layers twice. RULU was used as the activation function. Finally, we use softmax function to get 10 different probabilities. This is evaluation. This is a diagram showing the validation of the probability and the loss of learning using the previous model. The accuracy of validation data is 97.31% and the loss is 0.1312. We use batch size 64 and optimizer is Adam. It ended early with 21 epochs. It is a table of validation accuracy and FPS value when the input image and the model are changed. The highest accuracy was achieved was 64 by 64. Increasing the size of the input image throws the inference FPS, making it for real-time control. Since the goal is to achieve high accuracy this time, we adapted a 64 by 64 input images, even if a little low. This is a confusion matrix of inference of test images using a trained model. Also, there were some mistakes. It could be recognized with high probability. This is conclusion and future work. This presentation presented hand sign recognition using deep neural network. We were able to create a high precision model since the execution speed FPS has not been optimized yet. We plan to use hardware to execute it at higher speed and with lower power consumption. This is the difference. That's all my presentation. Thank you for your attention.
Thank you so much, Naoto. So we're gonna move forward with questions from the audience.
Yeah, thank you. Thank you for an exciting presentation. This is a very interesting topic. So I'm just wondering, the first question is, what is the role of the optimizer?
Optimizer.
Yeah, what is the role of the optimizer? What is the purpose of the optimizer?
Adam.
Yeah, what does it do? How does it help?
I adapt Adam because they use some optimizer in so was was able to get high accuracy in training. So I used the Adam optimizer
Okay,
in training.
I see. Okay, so that brings me to the next question. You are using the optimizer to get a high accuracy. So you are saying that with the image size increase, the accuracy is increasing, right? Image size. You did not mention the clarity of the image. Okay, what about the clarity of the image? You mentioned the size of the image, but you did not mention the clarity of the image in terms of the pixel or whatever, however you want to say it. So how would you explain that? Image size is increasing the accuracy. My question is, does image clarity also increases the accuracy? It should.
Do you understand the question?
Sorry, I cannot understand.
Can I try?
Yeah.
So I think we are just wondering. So this is related to the lung data, right?
Yes.
Yeah. Okay. So then the accuracy, how is the affected by the image clarity? So if the image is not clear or the image is clear, but in clear images, there is some images are more clear than other images. It's continuous. It's not binary. It's just this image is clear, this is a little more clear, this is a little more clear. So does clarity, the clearness of the image, affect the accuracy? You said the size
Yes.
affects the accuracy, but the clarity of the image, does that affect the accuracy? Do you understand?
Okay. Yes, I understand
Okay.
your questions.
Okay.
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 But
Thank you.
I quality of image.
Maybe there's no clarity difference in the analysis. I mean, every picture equal in clarity
Yes.
in this system?
Yes.
Yeah. Okay. I see.
Sorry.
So there's no, it's not, you don't sort the clarity like, this is level 5, this is level 4, 3, 2, 1. You don't do that. It's just it's clear, right?
Yes.
Okay, I see. Does that help, Roy Sensei?
Yeah, I understand. Yeah, that helps. Thank you.
Yeah. Some people, I just want to say, maybe some people don't, I didn't know myself, I did not know the original data say something about the original, say, these are human evaluations. Being a person, a doctor or list, looks at the image and decides is clear or not clear.
Yeah. So I was,
Because
not sure.
we don't know we don't know the data source, so we didn't understand.
Yeah, right, exactly. Yeah.
Thank you.
Okay, thank you. Yeah.
That's good. Very interesting. Thank you.
Thank you.
Thank you. So is there any other question? I guess everything is clear now. So we can officially finish our morning session. So thank you to both laboratories, robot engineering and adaptive systems laboratories. Much interesting topics and talks. So I guess we're gonna take a lunch break and resume our presentations later in maybe a little bit more than 2 hours. Yep.
Yeah, 2 hours.
So thank you everyone for your time, for your presentations, and we will see each other later today, tonight, or whatever the time it is for everyone.
Okay, thank you very much. Yeah,
It's almost 4 o'clock here.
Wow. So 4 hours ahead. Yeah, yeah. Okay.
In New
Nice. For us, it's 9 p.m.
Yeah.
Oh, that's late.
Yeah. It's still a good time.
Yeah.
But yeah, it was a quite interesting experience, Devo. You know, to have this event with people all around the world.
I know. It was exciting. Yeah, just to manage the time zones was a big headache. You know.
Yeah, I was talking to Christina that she told me I haven't seen the Germany guys, and I'm like, whoa, because when
they're sleeping.
yeah, exactly. When we are presenting is their midnight time, and maybe when they're presenting it's also our midnight time. So it's,
I know.
You know.
Yeah.
But you know, in Mexico, Mexico, it's very bright at 9 o'clock at night. I can see in the background there, it's bright daylight.
Yeah, it is right.
Hiram couldn't get back home. He's still on the campus.
I'm still in the campus. Yeah. Open space, so that's why I came here to, you know, like the garden of the university, the campus.
Oh, great.